All right, this is the video for the grad student only problems from homework number 1. And the first of those was exercise A1.3. So we're going to start with part A. So each of these is a proof of the following sets of properties of different set operations. And the first one is to prove that the complement of the intersection of A and B, or A intersect B complement, is equal to A complement union B complement. Now, because this is an inequality, what we have to prove, first that A intersect B complement is a subset of A complement union B complement, right? And we also have to prove that A complement union B complement is a subset of A intersect B complement. So we'll start with part 1. So proof of 1. Okay, so first of all, we're going to start with letting some x be an element of A intersect B complement. And if that's true, that implies then that x is not an element of A intersect B. That's basically the definition of a complement. If x is an element of this complement, it means it's not in A intersect B. And that is to say, or rather, if this is true, then either x is not an element of A or x is not an element of B. And x is not an element of A, and it's also not an element of B. If that's true, then x is an element of A complement, and x is also an element of B complement. Both of those things have to be true. All right, so since if x is an element of this A intersect B complement, then it's also an element of this set. So we've just proven that A intersect B complement is a subset of A complement union B complement. All right, so there's proof of that first statement there. Now we just have to prove this second part. All right, so proof of 2. Oops, not of. Proof of 2. So same thing, we're going to start with some x that's an element, this time of this set, A complement union B complement. And this implies, by definition of what a union is, that x is an element of A complement or x is an element of B complement. Now that implies that x is not an element of A or x is not an element of B, right? By definition of what a complement is. Not an element of A, right? Now this implies that x is not an element of A intersect B. And it's probably easiest to see this visually. So if we have a universal set to which A and B both belong, Here's A and here's B. The circles A and B. The sets A and B. X is not an element of A. Is going to be all of that. Or X is not an element of B, which is all of that. And as you can see, the only thing that's not shaded is the intersection of A and B. So X is not an element of A intersect B, right? So that's kind of a visual proof. Okay, so if X is not an element of A intersection B, then another way of saying that is X is an element of A intersect B complement. Okay, so now what we've proven is that any element X that's in this set is also in this set. So we have proven that A complement union B complement is a subset of A intersect B complement. Right? All right, so there we go. We've proven it in both directions. We've proved that each of these is a subset of one another, and so they are equal. There you go. That's the proof for part A. Okay, so the proof for part B of A 1.3 is pretty similar. Right, we have to prove that A union B complement is equal to A complement intersection B complement. And so again, we're going to have to do this in two parts because we have to prove that this is a subset of this and that this is a subset of this. So for any X that's an element of A union B, let me take a step back. Just so we're super clear here, right? We have to prove, first of all, that A union B complement is a subset of A complement intersect B complement. And we have to also prove that A complement intersection B complement is a subset of A union B complement. So proof of one, start with the first part. So we have some X that's an element of A union B complement. And that's another way of saying that is that X is not an element of A union B. And if that is true, then that implies that X is not an element of A and also not an element of B. So all other elements outside of these two sets added together, right? Another way of stating that, right? This basically implies that X is an element of A complement and X is also an element of B complement. So that excludes everything that's in A and B. And this basically is the definition of intersection, right? So this implies that X is an element of A complement intersection B complement. And so what we've just proven is that any element X that's an element of this set is also an element of this set. And so we have just proven that A union B complement is a subset of A complement intersect B complement. So we just proved part one there. So now we just need to prove the second part. So if X is an element of A complement intersect B complement, then it has to be true that X is an element of A complement and is also an element of B complement. Now, if that's true, then X is not an element of A, and X is also not an element of B. That basically implies that X is an element, or rather, X is not an element, I suppose, of A union B. And that's simply the definition of a converse. So X is an element of A union B complement. And so we now have proven that any X that's in this set is also in this set. So we have proven that A complement intersect B complement is a subset of A union B complement. All right, so there we go. We've proven both of these things, so it's true that they are equal. All right, this is the proof of the last part C of A 1.3, where we have to prove that A intersect B union C equals A intersect B union A intersect C. And just like the previous two, we have to prove that this is a subset of this and this is a subset of this. So we have to prove that A intersect B union C is a subset of A intersect B union A intersect C. So that's part one. And we also have to prove the other way around, that A intersect B union A intersect C is a subset of A intersect B union C. So we'll start with part one. So if X is an element of A intersect B union C, then that implies that X is an element of A, and X is also an element of B union C. Now, X being an element of B union C implies that X is an element of B, or X is an element of C. Let's see. All right. So basically what we have now is that X is an element of A, and x is an element of B, or x is an element of A and C. So we can write that, right? This is just the intersection. Both of these are the intersection. So what this applies is that x is an element of the intersection of A and B, or x is an element of the intersection of A and C. And of course, this is just the union, right? This is the union of these two things. So x is an element of A intersect B union A intersect C. And so we have now proven that if x is an element of this set, it's also an element of this set. And that implies that that implies that the set A intersect B union C is a subset of A intersect B union A intersect C. Now for the second part, if x is an element of A intersect B union A intersect C, then what that implies is that x is an element of A and B, or x is an element of A and C. We can also state that as x, in fact, that implies that x is an element of A, and x is an element of B, or x is an element of C. That implies that x is an element of A and x is an element of B union C, right? Because this is just the definition of a union. And this is the definition of an intersection. So x, therefore, is an element of A intersect B union C. And we have just proved the equality in the other direction. We've proved that this is a subset of this, right? So therefore, A intersect B union A intersect C is a subset of A intersect B union C. So we've proven it in both directions. They're each subsets of each other, and so they are equivalent sets. Okay, now we're going to prove, this is exercise A1.7, where we have to prove using induction that n is less than 2 to the n power for all n that are elements of the set of natural numbers or counting numbers. So 1, 2, 3, etc. So we're going to start by assuming that n equals 1, and we basically get 1 is less than 2 to the 1 power. And that's true, of course, right? 1 is less than 2. Now we're going to assume that n equals k, and that this is true for n equal to k. So k is less than 2 to the k power. And therefore, if we multiply both sides by 2, we get that 2 times k is less than 2 times 2 to the k power, which is equal to 2 to the k plus 1. And this implies, right, I'm going to break this out. This implies that k plus k is less than 2 to the k plus 1. Now, I forgot to mention, and this is assuming that k is an element of the set of natural numbers, right? All right, so since k is an element of the set of natural numbers, k plus 1 is going to be less than or equal to k plus k, which is strictly less than 2 to the k plus 1, and therefore k plus 1 is strictly less than 2 to the k plus 1 for all k elements of the set of natural numbers. Okay, so it doesn't matter what k is for any value of k, and therefore any value of n, this is true. And that's proof by induction.